A universally unique identifier is an identifier standard used in software construction. A UUID is simply a 128-bit value. The meaning of each bit is defined by any of several variants. A human-readable display. Many systems use a canonical format using hexadecimal text with inserted hyphen characters. For example, 123E 4567E89 B12D3A 456-426,655,440,000. The intent of UUIDs is to enable distributed systems to uniquely identify information without significant central coordination. In this context, the word unique should be taken to mean practically unique, rather than guaranteed unique. Since the identifiers have a finite size, it is possible for two differing items to share the same identifier. This is a form of hash collision. The identifier size and generation process need to be selected so as to make this sufficiently improbable in practice. Anyone can create a UUID and use it to identify something with reasonable confidence that the same identifier will never be unintentionally created by anyone to identify something else. Information labeled with UUIDs can therefore be later combined into a single database without needing to resolve identifier conflicts. Adoption of UUIDs is widespread, with many computing platforms providing support for generating UUIDs and for parsing, generating the textual representation. Definition: a UUID is a 16-octet number. In its canonical form, a UUID is represented by 32 lowercase hexadecimal digits, displayed in 5 groups separated by hyphens, in the form 8444124 for a total of 36 characters. For example, 123E 4567E89 B12D3A 456-426,655,440,000. The first 3 sequences are interpreted as complete hexadecimal numbers, while the final 2 as a plain sequence of bytes. The byte order is big-endian. This form is defined in the RFC and simply reflects UUID's division into fields, which apparently originates from the structure of the initial time and MAC-based version. The number of possible UUIDs is 1632, which is 2128, or about 3.4 times 1038. Variants and versions. A UUID is formatted according to a specified variant and a specific version of the variant. The variant indicates the layout of the UUID. The UUID specification covers one particular variant. Other variants are reserved or exist for backward compatibility reasons. An example of a UUID that is a different variant is the Nil Uuid, which is a UUID that has all 128 bits set to 0. In the canonical representation XXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXX UUID specification is indicated by the two most significant bits of N being 10. RFC 4122 variant. The variant covered by the UUID specification has 5 versions. For this variant, the 4 bits of M indicate the UUID version. Each version uses different information to generate the UUID, and thus some may be more appropriate than the others in specific use cases. According to the specification, version 1 UUIDs are generated from date, time and MAC address. The version 2 UUIDs are generated from group A user ID and date time. The version 3 and AMP5 5 produces deterministic UUIDs generated from a user-specified namespace and user-supplied data, and version 4 is generated from pseudo-random number. The version 1. Conceptually, the original generation scheme for UUIDs was to concatenate the UUID version with the MAC address of the computer that is generating the UUID, and with the number of 100 nanosecond intervals since the adoption of the Gregorian calendar in the West. By representing a single point in space and time, the chance of a collision in values is effectively nil. This scheme has been criticized in that it is not sufficiently opaque. It reveals both the identity of the computer that generated the UUID and the time at which it did so. Its uniqueness across computers is guaranteed as long as MAC addresses are not duplicated. However, given the speed of modern processes, successive invocations on the same machine of a naive implementation of a generator of version 1 UUIDs may produce the same UUID, violating the uniqueness property. Version 2. The version 2 UUIDs are similar to version 1 UUIDs, with the first 4 bytes of the timestamp replaced by the user's POSIX UID AGID and the upper byte of the clock sequence replaced by the identifier for a local domain. However, version 2 is not explicitly defined in the UUID specification and thus is not implemented by all UUID generators. Version 3. The version 3 UUIDs use a scheme deriving a UUID via MD5 from a URL, a fully qualified domain name, and object identifier, a distinguished name, or on names in unspecified namespaces. The version 3 UUIDs have the form XXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXX A or B. According to the specification, version 3 exists for backwards compatibility. If backward compatibility is not an issue, SHA-1 is preferred. To determine the version 3 UUID of a given name, the UUID of the namespace is transformed to a string of bytes corresponding to its hexadecimal digits, concatenated with the input name, hashed with MD5 yielding 128 bits. 6 bits are replaced by fixed values. 4 of these bits indicate the version 0011 for version 3. Finally, the fixed hash is transformed back into the hexadecimal form with hyphens separating the parts relevant in other UUID versions. Namespaces are themselves UUIDs, while the UUID specification gives example UUIDs for namespaces corresponding to fully qualified domain names, URLs, ISO IDs, and X500DNs. Any UUID can be used as the namespace when generating version 3 or 5 UUIDs. Thus, nesting of namespaces is possible. The version 4 UUIDs are defined by RFC 4122. These UUIDs depends primarily on random numbers. This algorithm sets the version number as well as 2 reserved bits. All other bits are set using a random or pseudo-random data source. The version 4 UUIDs have the form XXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXX A or B. The version 5 UUIDs use a scheme with SHA-1 hashing, otherwise it is the same idea as in version 3. RFC 4122 states that version 5 is preferred over version 3 name-based UUIDs, as MD5's security has been compromised. Note that the 160-bit SHA-1 hash is truncated to 128 bits to make the length work out. An erratum addresses the example in Appendix B of RFC 4122. Standards. Uu Ids are standardized by the Open Software Foundation as part of the distributed computing environment. Uu Ids are documented as part of ISO IEC 11978-1996, Information Technology, Open Systems Interconnection, Remote Procedure Call, and more. Recently in ITUT-REC. By .667 ISO IEC 9834-8/2005, the IETF has published the standards track RFC 4122 that is technically equivalent with ITUT-REC. By .667 ISO IEC 9834-8. History. Uu Ids were originally used in the Apollo network computing system and later in the Open Software Foundation's distributed computing environment. The initial design of DCE Uu Ids was based on Uu Ids as defined in the Apollo computer network computing system, whose design was in turn inspired by the unique identifiers defined and used pervasively in Domain OS, an operating system also designed by Apollo Computer. Later, the Microsoft Windows platforms adopted that design as globally unique identifiers. Other significant uses include ext2, ext3, ext4 file system user space tools, Lux encrypted partitions, GNOME, KDE, and Mac OS X, most of which either use the liborowd library now provided by the util Linux package or implementations derived from it or from the original implementation by Theodore TSO in the E2F's progs package. One of the uses of Uu Ids in Solaris is identification of running operating system instance for the purpose of pairing crash dump data with fault management event in the case of kernel panic.